Hi, I'm Cosimo Gregucci, and it's my great pleasure to introduce our paper Is Complex Query Answering Really Complex? Our work relies on knowledge graphs, where information is encoded as triples. Here you see a snapshot of Freebase 15K237, where the different colors correspond to different relation types in the graph. For example, when in Rome is distributed on Blu-ray, I Am Legend was filmed in New York City, and Kay Chandler performed in King Kong. Such knowledge graphs can be queried. For instance, the question which actor performed in a movie filmed in New York City and distributed on Blu-ray can be represented in the 2i 1p graph format because it involves an intersection of two links and one path prediction 1p. Using classical solvers, we perform graph matching to answer the query. In this case, the only actor satisfying the constraints is E. Thompson, who appeared in I Am Legend, a film that was both shot in New York City and released on Blu-ray. But knowledge graphs are incomplete. The solid links represent the observed graph, so the training, whereas the dotted links show missing links, essentially the test triples. When the graph is incomplete, classical solvers will inevitably miss some answers. To predict answers in incomplete knowledge graphs, the task called complex query answering (CQA) has arisen. Its goal is to recover the highlighted answers even when some links are missing. CQA has attracted considerable attention, and many methods have been proposed. What we argue in this paper is that query answers are not all equally hard. Depending on the number and position of the missing links, predicting an answer can be easier or harder. If only one link is missing, as with the K-dust in the example, the original 2i1p query reduced to a simple 1p. If two links are missing, the query answer reduced to either 2p or 2i, depending on where in the query graph the missing links are. If all links are missing, the query answer cannot be reduced to any other type. Intuitively, there is an hardness spectrum. 1p is the easiest and the non-reducible 2i1p the hardest. This reduction applies to any query type. So, our first question is, how is the hardness distributed in existing benchmarks? We analyzed the popular Freebase 15K237 and NEL 995 benchmarks and found that the vast majority of query answers belong to the easiest 1p reduction. Looking at the highlighted diagonal, only a few percent fall into the hardest category, where full prediction is required. This skewed distribution is the result of assuming triples are independent, which ties the benchmark directly to an artificial percentage of missing links. Now, we are curious to see whether this imbalance in benchmark affects state-of-the-art performance and to verify empirically that an hardness spectrum exists. Both statements are true. In fact, the table shows the results for the different reduction of a 3p and 2i1p query. MRR performance drops sharply when all links need to be predicted, as shown in the highlighted columns, and because 1p reduction dominate current benchmarks, the overall scores reported so far mainly reflect performance on them. This means that current CQA benchmarks are not suitable for precisely assessing CQA methods. So, how can we construct benchmarks that are instead suitable for it? Our proposal is to correct the skewed distribution by breaking the triple independence assumption. Returning to the 2i1p example, almost 97% of its answers are reducible to 1p and only 0.1% are non-reducible. To address this imbalance, we build a new benchmark by sampling query answers so that the full spectrum of hardness is equally represented. We do so for all query types. The performance in the new versus old benchmarks show a significant drop. For example, 3i queries on Freebase 15K237 fall from about 50% to below 15% MRR, and we can see that such a drop in performance consistently happens for every query type in the benchmarks. And even more surprisingly, there is no clear SOTA in the new benchmarks, as the table, including many SOTA baselines, reveals. This suggests that current methods have mainly focused on improving performance on the easiest query answers, and therefore we still have some work to do. Thank you.